quick, but I'm guessing based on the lecture, a couple lectures last week, 2 lectures on nuclear, you've come up with some solid pros and cons. Maybe some of the things you want to characterize as uncertainties as well. So, who would like to offer the first pro? Any pros? Yeah.
Great energy density.
So the fuel is energy dense, yeah. It's like 1,000,000 times more dense per kilogram, right? That's the first problem set. Yes, Ryan, and then.
Does not emit CO2 in this normal operation.
Okay. So, let's call it low life cycle carbon emissions. Yeah.
It's also energy efficient, as in like they run at higher capacity factors.
Okay, well that's 2 different things then. Remember, don't get mixed up on efficiency and capacity factors, but they do run at high capacity factors, which means it's base load power. They actually still have a thermal efficiency of around 33%. Yes, George.
Stable energy supply not easily affected by the season or weather.
Okay, stable. Any other pros? We have some domestic fuel supply, maybe not an incredible amount, but we have some domestic supplies of uranium and other supplies in friendly countries like Australia and Canada, friendly Canadians. So let's move to cons. What are some cons? Yeah. Safety. Which kinds of safety?
So if you have any kind of accident, repercussions are usually huge.
Yeah. So like a meltdown or accident.
And then the facilities are vulnerable to attack of any kind.
Right. And so then maybe like the proliferation risk or attack, those could actually be 2 different things because there's different ways to where proliferation could occur in the fuel cycle. What are their cons?
I would argue that baseload is actually not flexible, but
So it's not flexible.
also they haven't figured out the waste storage.
Right, waste. Have to deal with the waste because it has harmful radiation, right? What's another con? So as you said, yeah.
Maybe it's highly centralized, so it's probably has like a lot of startup costs as well.
Yeah. Well, how would Amory Levins describe that one?
Hard path.
Hard path, right? Yeah, centralized, huge upfront costs, and technologically very complex. So we got some of the national security concerns and proliferation. Maybe the mining of uranium is damaging. Does anyone have any uncertainties they're thinking about with regards to nuclear power?
Cost of decommissioning.
That's a good one. Cost of decommissioning. Anything else? Yeah.
Safety of storage.
Safety.
Even
Yeah.
how they're going to store.
With storage, maybe the longevity of the storage. Really, is it going to be able to take care of it for 10,000 years or longer? Maybe. Yeah.
Environmental factors like earthquakes and tsunamis and stuff.
Okay, yeah. Earthquakes. Don't build nuclear plants near fault lines. It's like a basic one. And also, some of the next generation reactors, we're not really sure exactly what cost they're going to end up being. You know, people are saying it's going to provide low cost power forever, but really, none of those have been tested beyond certain scales. So when you do scale it up, we're not sure what the end cost will really be. Okay, I think we've hit on most of the major points. Let's, sorry, I got these clicker questions, wanted to do them first, but they are now warmed up. So get out your clickers. This will prime the rest of the lesson, fuel cycle and reactors. Okay. Nuclear fission is activated by which of the following? A neutron, electron, uranium-235, or plutonium-239? What? This clicker thing. It's really cool. You guys get an extra minute to think about this one. It's not. Okay. All right, so who has an idea of what the answer is?
It seems kind of tricky, but like you won't actually start the fission unless you have a neutron hitting the 235.
That's right. Yeah. So you need the uranium, but it's the uranium itself won't activate the reaction until it's hit with the neutron. Right, and we'll go over that in terms of the actual reaction shortly. Now it's working. So let's do. Let's do number 2, and then we have clickers for this one, so we can use those. Which of the following is a con of nuclear power? So you guys already had a hint on that one. Capital intensive hard path, safety, radioactive waste disposal, security, or all of the above. Your answers now.
Hey John,
9.
what's the frequency code for the iClicker?
I don't know.
And how do they connect to your base station?
I have 9 responses right here.
Oh,
Yeah. They connect every week now. You know what the code is. You provide codes?
I thought there is some like code like AA or AC or what you customize and then. Okay.
Well, everyone got it right, which means
Cool.
they were paying attention 5 minutes ago, which is good. Right, all of these are the cons that we just touched upon. Which of the following about half-life is not true? The half-life of an element is the time required for 1/2 of its unstable nuclei to decay. T1/2 equals 0.693 divided by K, where K is the decay constant. Given the half-life, we can calculate the percentage of remaining nuclei at any time. And then half-life varies with the element, or none of the above. So, enter your answers. Okay. Good job, guys. It is none of the above. So all of these, therefore, are true about the half-life. And we'll go over those equations shortly. Lastly, let's do one more. Yeah. Sure. Okay. Which of the following is not an advantage of nuclear power? High energy density, clean source of energy, decreased capital costs with technology innovation, promoted domestic energy supply, can serve as a base load generator. I wish we had that clicker working. This one's a little trickier. But maybe we can do show of hands. A. B. Couple of these. C. D. And B. Alright, so a couple folks said B, which I think is true. It's debatable because there's the waste. But C is the answer we're looking for here, as the costs have not declined typically for generation 2 reactors. Basically, it's stayed steady, and the promises of next generation reactors say that it should come down with technology innovation, but that's a big unknown because those have not been deployed yet. So that's our clicker questions. We've gone through this cons, pro, and uncertainty. Actually realized I got a topic. Let's do 3, the actual reaction. All right. So fuel cycle. There's actually a great chart in the handouts. So actually, I'll just pull that up. There, that's good. So this shows the whole fuel cycle from if we're taking raw uranium, we want to mine it first. Then it's converted to something called uranium hexafluoride, and then it's enriched for most types of reactors that use enriched uranium. Those are called the light water reactors. And once it's enriched, it's fabricated into different rods that can be placed in the reactors, right? Then within the reactor, it's bombarded with neutrons, setting off a chain reaction that's controlled with control rods. And then at the end, you get a bunch of heat, which heats up water and makes steam and turns a turbine like we're familiar with. So instead of combustion, it's the reaction and energy created from the nuclear reaction that's heating up the water. But then we have spent fuel, so all of the other radiation products from the nuclear reaction. That can go into temporary storage and then a long-term waste repository. Or it could go to fuel recycling. So different countries have different policies on fuel recycling. France does a high amount of fuel recycling, and they'll recover a lot of uranium that can be enriched and then send right back into the fuel fabrication and to the nuclear plants. There's also another type called mixed oxide or MOX fuel fabrication, which is a combination of plutonium and uranium. And I believe what they're trying to do there is to have a fuel that can use both, or have a type of reactor that can use both plutonium and uranium products, because then it takes the plutonium out of storage, because plutonium is something that you can more easily make weapons from. And so we're trying to take that and not have it in risky storage places where attacks could occur or theft could occur and potential proliferation risk could increase. Yes.
Do you know what some of the reasons why recycling policies may vary between countries?
Yeah, so I think it's a factor of price and economics. It's a factor of having long-term waste depository sites and what are the policies with regards to those. And then also the nuclear proliferation piece and how the country views that as a threat or not. So this is your fuel cycle. So I think, yeah, it's good to think about the economics both of mining and fuel recycling. It's useful to think about that proliferation risk for having plutonium stored somewhere. And then it's also, obviously, you need to think about what type of reactors you're using, and we'll go into that in 1 second. Yeah.
In class, you talked about enrichment just being separating 235 and 238, but is there something else besides just centrifuging or anything else?
Yeah, it's the percentage of uranium-235 that's in the fuel.
But so they're just, that's the only thing they're changing, they're not.
That's right. Yeah, they're changing the concentration of that isotope specifically. So that's the fuel cycle. So the reaction. So in the reaction, so we have uranium-235. That's the most typically used nuclear fuel. We're going to bombard it with a neutron. And we're going to get out a couple different things on the right side of the equation. So we're going to get some plutonium. We're going to get some other product. I forget what it is. It's actually not on the sheet. Then we're going to get 2 neutrons, and we're going to get energy. This is, if someone wants to Google it. And so we need to be able, these isotopes could have very active radiation lifetimes, and it's going to be our end spent fuel products, right? The ones that we have to take care of and store because they have harmful radiation, right? And but the fact that you get 2 neutrons out means that the reaction can self-propagate, right? So it's going to, those neutrons are going to bombard with more uranium, and it's going to set off a chain reaction. Now 2, 4, 8, 16, 32. How do we control that? There's specific control rods within the reactors that make sure that it gets up to a sustainable level but does not go above that level. And then this is what we really want. This is the energy that is part of the fission reaction that comes out. It's a very small number for just one reaction. It's like something like 1 × 10 to the -11 joules or something. It's 200 million electron volts, where an electron volt is 10 to the -18 or something. And but since we're getting so many reactions, and we can get so many reactions for even just a kilogram of the substance, it's going to end up producing a lot of energy. And we use to heat water, make it into steam, and then it turns into turbines similar to just like a fossil fuel plant. Right. So that is, I wouldn't worry about knowing anything too much more complex than this.
I don't think plutonium is made in fission. I think it comes from a neutron capture reaction in uranium. Usually, like, you have 2 much smaller, lighter elements that come from fission.
Right,
So
okay.
it's like xenon and like something else.
Right, and they might make some other side reaction, is what you're saying? To
So-
form plutonium?
So plutonium isn't really made in fission, it just comes like, if you don't fission the uranium, if you capture on uranium-238,
Okay.
then you create plutonium. But if you fission U-235, it's two elements that are like 1/3 and 2/3 the mass of uranium. So around xenon and around something else.
Okay.
One clarification, actually the plutonium comes from fission, but comes from U-238.
Yeah, it comes from the capture of uranium-238. So that's not fission, it's a neutron capture reaction, not a fission reaction.
Neutron capture reaction.
So
Yeah.
U-238, adding a neutron, capturing a neutron.
Yeah, plus a neutron.
Makes
Then-
some sort of plutonium.
Yeah, makes
Right.
plutonium.
Okay, that's
But
great.
if you fission U-235, you make two things that are not.
Right, these are like radium and something else.
Yeah.
right?
Like xenon or something like that.
Cesium, I don't know,
Like
something like
maybe
that.
Or cesium or something like that.
Yeah, so, thankful, that's a very helpful explanation because the fuel is, the type of fuel and reactor that you have is all about the various concentrations of these two elements. Right. So that's the reaction, so let's talk about that, the reactor types. So first we have the light water reactor. Make some space here. So the light water reactor, LWR, accounts for about 90% of commercial reactors in the world. And this one uses a fuel that's enriched to about 4 to 5% uranium-235. So the rest of it is mostly uranium-238. But you're enriching up to 4 or 5% uranium-235. That's the product that you want for that reaction. Then a heavy water reactor is only enriched up to 0.7% uranium-235. And so it's a lower enrichment, but when you're using heavy water, basically it has, this heavy water has, I believe, more neutrons in it, so it has greater neutron economy. So therefore you don't need as much fuel enrichment to have a similar amount of reactions. And then in terms of the, this is 90% of all the reactors is the light water reactor. And then there's two types from there. The boiling water reactor and the pressurized water reactor. The main difference here, it's you don't really need to know it too in depth, but essentially the pressurized water reactor doesn't boil the water within the reactor itself. So that boiling is kind of taking place in a heat exchanger next to the reactor, rather than in the reactor itself, where the boiling is actually taking place in the reactor as well. But I believe the PWR is the more popular reactor. Pressurized. So those are the reactor types: light water and heavy water, and within that, the light water, boiling water, and pressurized water reactors. And this one is differentiated by the enrichment level of uranium. Since this one uses heavy water, it has greater neutron economy. So same amount of reactions, but fewer uranium-235. And then this is differentiated by where the actual boiling of the water is taking place in the reactor, or kind of in a heat exchanger next to the reactor. So with that, I think we can do a problem that will kind of look at the dynamics of this reaction and then and half-lives, and then one that looks at kind of the amount of fuel that we need to create for 1 gigawatt power plant. So first, let's do let's introduce basically the half-life equation. So I equals I naught equals delta T. So this is a similar form to some other equations we've seen throughout the class. Basically, the radioactive decay is an exponential process. So this is the number of decays at any given moment, I, based on the initial decay rate, the time, and then some decay constant, which is unique to the elements, and is the natural log of 2. So when I over I naught equals 2, right, for it to decrease by half over the half-life. So T sub 1/2 flat. So you can use this for the decay rate I. You can also use it just for the concentration. And it's the same. So this example problem 1 says plutonium is created by the decay of uranium-239 into plutonium-239, and ultimately to other plutonium isotopes. Plutonium-239 has a half-life of 24,000 years. That's why we have to store this stuff for such a long time. A large nuclear power plant produces half a ton of reactor-grade plutonium per year, about 60% of which is plutonium-239. So how much of that plutonium-239 produced in 2009 is going to be still going to be around in the year 10,000, which is just crazy to think about. So we're going to use our formula here. And we could say that the half-life is given, it's 24,000 years. So first we can solve for our lambda constant, which is the natural log of 2 over that half-life. So it's basically natural log of 2 over 24,000 years. So that's 2.9 times 10 to the minus 5 per year. And then we can plug our various numbers into the equation, since so our time is simply going to be the year 10,000 minus 2009, present day, 797,991 years. And then so C naught is going to be, so we said we had half a ton, 0.5 tons of reactor grade plutonium, 60% of which was this isotope. So 0.6 times the 0.5 tons. So that's just 0.3 tons. So we're going to plug this in, right? 0.3 tons, C naught, e to the lambda, which we have here, and then the time we have here. It all works out to be 0.24 tons. So 8,000 years have elapsed, and we've only gone down 0.06 tons. So this is really a long-term storage problem. It's our children's 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 children's